IVT worksheet. So we're going to use IVT in this worksheet to solve the questions ahead. So it's paramount to know what IVT is. Remember, IVT says if you have a continuous function from A to B, that every value between A and B, every y value between A and B must be used. So that's all it is. If you have a continuous function between A and B, every y value between A and B must be used. Everything above it, maybe. Everything below it, maybe. But the values here must be used. So if I'm going to show something we use in IVT, I need to do a couple things. We got to first say it's continuous, or show it's continuous. We got to second, we got to show that f of c is between the two values, so between f of b and f of a. And then we could go by IVT, the statement is true. So it's always show it's continuous, show that the values are in between the two things, and then by IVT. So look at the first one here. Use IVT to show that f of x is equal to x cubed plus x takes on the value of 9 for some x between 1 and 2. So first we got to say this is continuous. Why is this continuous? Well, this one is a polynomial function. So we're just going to go since f of x equals x cubed plus x is a polynomial function, it is continuous. So we got the first step done. We show it's continuous. Next, we want to show that 9 does fall in between these two. But to do that, we gotta do a little like off work here. So let's erase some of this because we have that down. Let's do some work to make sure we're true. So let's plug in these endpoints and see what happens. Here what f of 1 is. If I plug 1 into here, I get 1 cubed plus 1. So 1 plus 1 is 2. Let's plug f of 2 in here. F of 2, I get 2 cubed plus 2, so I get 8 plus 2, so 10. Doesn't 9 fall between those two? So it is. So it is going to be true. 9 is going to be between these two values. So all we got to say is, okay, now that we know f of 1 equals 2 and f of 2 equals 10, so 9 is going to fall between these two values. So what the thing is, we're not going to say 9 is between 2 and 10. That's obvious. You got to use these values instead. So you're going to say f of 1 is less than 9, which is less than f of 2. Right? Because we're talking about 1 and 2 here. So we want to show that the y values of 1 and 2 are below and above the 9 we want. So we have that part down. So now we got to say is by IVT is this true. So now by IVT, there is some c in 1, 2, the interval 1, 2, such that f of c equals 9, which is what we're trying to show. So that's all it is. I know it looks like a big old paragraph, but that's all it is. It first always show that it's continuous. There's different reasons why it might be continuous on the domain. So it's continuous on this domain here because it's a polynomial. Then show that endpoints do in fact go around the value they give you. It's going to work because that's why we're showing it. And then third, say by IVT this holds, so it's true. So let's try it again. So g of t, so that g of t equals t over t plus 1 takes on the value of 0.499 for some t in the thing. Okay, so first we gotta say it's continuous, but like you might go, wait, that's not continuous. That's a rational function. But where is it discontinuous at? The vertical asymptotes, right? Where t plus 1 equals 0. So it's discontinuous at t equals -1. But look at our domain. It's only 0, 1. So we don't have to worry about it. Like the graph here looks like this. So between 0 and 1, what we're looking at, we're totally continuous. So all we have to say is, since g of t equals t over t plus 1 is rational, it is continuous on 0, 1. Right, rationals are one of the known continuous functions. It's not continuous everywhere, but as long as you're not in between it, as long as the interval doesn't take over where it's discontinuous at, then you're fine. So since g of t is rational, it's continuous on this interval. Totally fine. And then we do what we always do, right? Next we do is check these endpoints. What happens when I plug in? Do some off-board work here. What happens when I plug in 0? I get 0 over 0 plus 1, which is just going to be 0. When I sub in 1, I get 1 over 1 plus 1, which is 1 over 2. So 0.4499 is less than 0.5 and is more than 0. So it does fit. So we go to the next step. Now g of 0 equals 0 and g of 1 equals 1/2. So, right, we're going to say that 0.499 is between these two, but we don't use these values, we use these values. I said we don't use this notation, we use this notation. It's less than 0.499, which is less than g of 1. That. And then we go by IVT. There is some c in 0, 1 such that g of c equals 0.499. I could put 29s. So there we go. Right, so it's the same concept every single time when we do this. Show it's continuous, and then show that your endpoints you have actually do hold, that one entire one's like that the number you're trying to show is between those two values, and then say by IVT. Next one. So g of t equals t squared tan t takes on the value of 1/2 for some value of t between 0 and 4. So same concept. So I know tan is not always continuous, but it is continuous between 0 and pi over 4. So we're going to say, since g of t equals tan squared, tan t is the product. Oh yeah, I should front that, right? Notice that's also times by tan squared. So this tan squared is a continuous function. Tan is a continuous function between 0 and pi over 4. Tan is not continuous at pi over 2. And so we're still good. So as long as this is continuous and that's continuous, we're good. So we're just going to say since t squared times t is a product of two continuous functions, probably should be a little more detailed. A product of a polynomial function and a trig function it is continuous. Okay, next, let's do the work and see what the endpoints give us. What happens when I plug in g of 0? I'm going to get 0 squared times tan of 0. Tan of 0 is this 1, so it's 0 times 1, so it's just 0. G of 1, pi over 4, sorry. I'm going to get pi over 4 squared times tan of pi over 4. Tan of pi over 4 is this 1, so I get pi over 4 squared times 1, or just pi squared over 16, I guess. And that is essentially like, remember pi is like 3.14, so this is about 9 over 16. So that is bigger than 1/2. Pi squared over 16 is about 9 over 16. Probably a little bit more than that, actually. So it's definitely more than 1/2. So it does hold. So next we say that, right? We say now g of 0 equals 0 and g of pi over 4 equals pi squared over 16, which is about 9 over 16. So g of 0 is less than 1/2, and that's less than g of pi over 4. So now we know that it's continuous, and the value falls between the two endpoints, so IVT does hold. So we go by IVT. There is some c in 0 to the power of 4 such that g of c equals 1/2. Let's do some more. We gotta make sure we know this. Show that f of x equals x squared over x to the 7th plus 1 takes on the value of 0.4. So it's a little tougher because it doesn't tell you what are your endpoints. So you gotta kind of come up with them yourself. So 0.4, what's something I could plug in here that would be less than 0.4? A good guess would probably be 0. Let's look at what happens when I plug in f of 0. I get 0 squared over 0 to the 7th plus 1, which equals 0 over 1, which equals 0. So that's the lower bound. We can put 0 as a lower bound. I didn't want to be negative because -1 is a bad number down here. -1 is it would be non-continuous. So let's go the other way though, right? What's an easy thing to plug into here? Well, we plugged in 0. So the next probably easiest thing would be 1. Let's try 1. F of 1 equals 1 squared over 1 to the 7th plus 1, which is 1 over 2. And 1 over 2 is bigger than 0.4. So there's our endpoints, 0 and 1. Other than that, we're treating it the exact same way. Step 1, show it's continuous since f of x is a rational function it is continuous on 0 to 1. Which is true. It is continuous from 0 to 1. It's not continuous everywhere, but it is continuous from 0 to 1. And then now we know what next we say what the endpoints are. Now f of 0 equals 0 and f of 1 equals 1/2. So f of 0 is less than 0.4, which is less than f of 1, which is 1/2. So now we can say by IVT that 0.4 does fall between 0 and 1 in this thing here. So by IVT there is some c in 0 to 1 such that f of c equals 0.4. Right, so it's a similar idea, just you have to come up with your own in that case. Next one, show that cosine of x equals x has a solution in interval 0 to 1. Here's the hint though, show that f of x equals x minus cosine of x has a 0 on 0 to 1. So that's the trick to this. So we're looking at this. So first let's do a little side work like we always do here. So if I'm going to use this as a hint, x minus cosine x, because the solutions means you hit 0. So if you have a solution, that means that there should be 0. Essentially, we're looking for a 0 between these two things. And we're going to use this as a version to get that. Right, solutions means they cross. So that means if you like subtract it over, you should get a 0 here. Has a 0 on the interval. So that's what we're looking for. 0 is what we're trying to go between. So let's put the endpoints and see if it works. What happens if I do f of 0? I would get 0 minus cosine of 0. Remember, cosine of 0 is 1, so I do get -1 in that case. If I do f of 1, I get 1 minus cosine of 1. Well, 1 minus cosine of 1 is not, cosine of 1, I don't know what that is, but it is a small decimal, so it's 1 minus some small decimal. So it does work. It's just some positive number. So it does work. We have a negative and a positive, so there must be a 0 between those two values. That's the way it works. So let's do what we normally do. It'll show this is continuous. How do we do that? Well, it's a difference of two continuous functions. We have a linear function that's continuous, and we have a trig function that's continuous. Well, cosine is always continuous. So you say since f of x is the difference of a polynomial and a trig function, both of those we know are continuous, it is continuous. Right, so that's the first step. Always say it's continuous. Why it's continuous? It's always to me because it's a function we know that's continuous. Second, let's show our values here. So we're going to say now f of 0 equals -1 and f of 1 equals 1 minus cosine of 1, which is a positive number. So look for 0, right? So f of 0 is less than 0, which is less than f of 1. So then we could go by IVT. There is some c in 0, 1 such that f of c equals 0. So f of x has a solution. To x equals cosine x. And got a little ugly there, sorry about that. Next one. Use IVT to find the interval length of 1/2 containing a root of this. So interval length of 1/2 means that you're going to go from like 0 to 1/2, or -1/2 to 0, or 1 to 1.5, right? It just means stuff that has the length of 1/2. A root is a 0. And the way we find that, we're looking for a sign change. That's how you know it's a root. So we want, like, when we plug in 0 to be a positive, when we plug in 1/2 to be a negative, something to that effect. We want a sign change. That's what does it. So we gotta do a little side work. We gotta find interval. So let's try these first. F of 0, so 0 cubed plus 2 times 0 plus 1. That just gets me 1. That's a positive number, so I need a negative. If I plug in f of 1/2, it's all going to be positive, so that's not going to work. That's all positive values. So what if I try -1/2? I get -1/2 cubed plus 2 times -1/2 plus 1. I get -1/8 minus 1 plus 1. So -1/8. So it does work. If I go, this one would work. F of -1/8 gets me 1/8. -1/8. F of 0 gets me 1. So that's my interval, that's 1/2. Other than that, we're going to do everything else the exact same thing we've been doing. So we got to write the whole thing. We go, since f of x is a polynomial, it is continuous on -1/2 to 0. It's a polynomial, so I can pretty much write it anywhere, but it's always nice to write, to make sure I'll write the little interval, just to be careful. Then you go, okay. So now I'll try to think what word we use. It doesn't really matter. It's just English. Now f of, now we'll start with the negative first. F of -1/2 equals -1/8, and f of 0 equals 1. So remember, a root is a 0, so we're just going to say f of -1/2 is less than 0 is less than f of 0. Then we can go, then by IVT, there exists a c between a c in -1/2 and 0, such that f of c equals 0. And then we want to finish it up a little bit, which means c is a root. That's what we're looking for. So you gotta say, like, right, we did all the work to show that it was 0, but what does 0 mean? 0 means it's a root. So we gotta do all that. Next one. Explain why f of x equals x squared takes on the value of 0.5 in the interval 0 to 1. So again, more of the same. Just more of this practice. So 0, 1. This is a I'm just going to do it real quick right here. Since f of, I should check the endpoints first. F of 0 is 0. F of 1 is 1. just plugging them into the equation real quick. So it does work. So faster. Since f of x is continuous. Oh, sorry. Since f of x is a polynomial, it is continuous. Now, f of 0 equals 0, and f of 1 equals 1. So, f of 0 is less than 0.5 is less than f of 1. Thus, by IVT, there exists a C in 0, 1 such that f of c equals 0.5. So there we go. Next one. The temperature in Vancouver was 46 degrees at 6 a.m. and rose to 68 at noon. What must we assume about the temperature to conclude that the temperature was 60 at some point? There's someone between 6 a.m. and noon. Well, if it went from 46 to 68, how do we know that it must have been 60 at some point? Well, this is IVT. Temperature must be continuous. Like there's no jumps. You can't go from 70 to automatically 90. You have to go all the values between. So we must assume temperature is continuous. What is the graphical expression of IVT? On the graph, so all this means is on a graph we can't skip y values. That's the whole thing, right? That's IVT says you can't skip y values. If you're doing a graph and it's continuous, all the y values must be used between the two endpoints. 4. Show that the following statement is false by drawing a counterexample. If f of x is continuous and has a root in a to b, then f of a and f of b must have opposite signs. Okay, so the trick here is that f and a are the endpoints. So let's say I draw two endpoints. Up here at like 3, that'll be my a, and then b will be over here at like, I don't know, 8. Right, so those are my endpoints. And you're trying to say, if I know there's a root between those two, that these two things must have opposite signs. That's not always the case. Remember, all IVT tells you is what happens between these two. I know that all these values must be used. But all at the top and the bottom are a maybe. We don't know. Right? All we know is that all the ones in between here must be used. We're not sure about everything else. Because the graph could look like this very easily. Something to that effect, and then you have two roots. But all these values between these two values still get used. Remember, that's all IVT tells you. So that's a counterexample. Right? Because remember, IVT doesn't tell you what happens in between the two roots. All we know is that these ones must be used. That's all it tells you. Everything else is a maybe. Okay. So now let's do a couple more problems with IVT. A car travels along the road with select velocities given a given table. So here's time, here's velocity. First question is, what term guarantees that at some time t, the car velocity is 35 feet per second? So, so it goes from 30 to 55. Velocity doesn't jump. You can't skip velocity, you have to go through all the values. So it's going to be IVT. Velocity is a continuous function. So IVT. Second question, what interval is the car guaranteed to be traveling between 35 feet per second? So between what interval? Because remember, you cannot pinpoint exactly where it travels that much, but we know it must happen between these two values. So between 15 seconds and 20 seconds. Right? I can't tell when exactly it hits it, but I know it's between those two intervals. Can you determine exactly when the car was traveling 35? No, we cannot. IVT is an existence theorem. Only. That just means that we know it exists. We can't tell you where though. We just know that it exists. Now, let me explain why there must be some time t. So this is like the whole thing again, right? So we gotta first say, since via t is velocity, which means it's continuous. Velocity is just known to be continuous. And, right, remember we always gotta do the endpoint, so we're doing 15 to 20. So, and f of, and well, we know 35 is between those two, because we know from here what it is. 35 is between via 15 and via 20. Remember, we use the proper notation. And via 15 is less than third. We can do the whole thing if we want. And via 15 equals 30. And via 20 equals 55. So via 15 is less than 35 and is less than via 20. Thus, by IVT, there exists a value t between 15 and 20 such that v of t equals 35. Okay, last page. Suppose f of x is continuous on negative 5 to 5. So from here, negative 5 all the way to 5. The following table shows selected values of f of x. Okay, so here's all the values from negative 5 to 5 of f of x. Plot the points in the given xy plane, and you connect the dots to this plane. So first, let's plot the xy plane. I guess I was supposed to give you an xy plane, but I don't have one, so let's do this. And 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay, negative 5 and 7. So negative 5 and 7. Negative 2 and 5. 0 and 2. 1 negative 1. 3 negative 2. 5 negative 5. So there's my plot. Can I connect the dots? No. This is just a table. I have no idea if it's continuous or not. Or I guess it is continuous. But I have no idea what happens between the dots. Right? So it could go up and down crazy and then connected. Go up and down crazy. Like, who knows? All you know is that these dots exist and it's continuous. This graph could be anything. Or it could be a straight line. Who knows? We don't. So no, we do not know how the function is behaving between the given values. Just like that. Formally explain, we're doing this again, why there must be a value of x between negative 5 and 5 such that f of x equals 6. Can the graph of f of x equals 6 more than 1 to explain? So let's do that formally part first. So f of x is continuous, like they told us as part of the problem right here, right? So I don't gotta show that part. I just gotta say since f of x is continuous, f is continuous, it's given, and right, we're trying to get 6. Let's look at what 5 is. 5 is 7, negative 5 is 7, and 5 is negative 5. So I'm going to say that this is between the two, but you got to watch out. I'm going to put this first. F of 5 is less than 6, which is less than f of negative 5. I know it looks a little funky, but f of 5 is actually just negative 5, and f of negative 5 is actually just 7. So this is a true statement here. So we could say by IVT, there is a value of x in negative 5, 5 such that f of x equals 6. Now, the second part, can the graph of f of x equals 6 happen more than once? Yeah. Remember, we don't know what happens in between these values. For all we know, it's constantly going up and down. So, yes. Because that's still the function. The graph of f of x can equal 6 more than once. Next one. What is the minimum number of times f of x equals 0 and why? Explain why is the minimum number of times. Well, look at our graph here. So the minimum number of times x equals 0 is 1. Because remember, all we're looking for is a change in sign. So from here it goes from positive to negative. So the minimum number of times is 1. On one time. On the interval. What's the interval of that? Between 0 and 1. Now, why is it the minimum number of times? Because again, we don't know what happens in between the values. So for all we know, it's going up and down, crossing I think a billion times. So we don't know. It's the minimum. Because we don't know what happens between the points. The given points. Can we conclude from the information of the graph of x is decreasing on 5, 5? Why or why not? For the same reason, right? It looks like it's decreasing, but again, we don't know what's happening in between these things. For all we know, the graph looks like this. Right? That's still a function. It's an ugly one, and that's not a decreasing function. We don't know what happens between the points. So no, and why I said, why we don't know what happens between the points. And that's this video.